Hello and welcome to the second in our series of webinars on high-temperature nanomechanical testing. Whether you're listening in from here in Europe or from further afield, and I can see we have participants from the States, Canada, Korea, Malaysia and Saudi Arabia, we trust you'll find today's presentation informative and relevant. In the discussion session at the end, our application specialists will be addressing some of the particular issues you indicated are of most importance to your organisations, but if you'd like to ask any further questions that come to mind during the webinar, please submit them in writing by typing in the dialog box on your screen. I'd now like to introduce our principal speaker, Professor Ben Beake, whose focus today is the use of high-temperature nanomechanical testing for optimising coating performance in challenging applications. Over to you, Ben.
Well, thank you very much, Alison. And as you said, we're going to be talking about using high-temperature mechanics. And we're going to be looking at one particular challenging application for coatings, and that is to deliver increased tool life in high-speed machining. So, conventionally, we measure the hardness of coatings at room temperature. So, however, this is not a good indicator necessarily of the tool life, and this is a good example. So this is a result of a cutting test, in this case end milling of a structural steel for two different coatings, for a 3 micron titanium aluminium nitride coating and for a 3 micron aluminium chromium nitride coating. And they're both the same stiffness, about 550 gigapascals, and they're deposited on the same cemented carbide substrate, and very closely modulus matched to that substrate. And in terms of hardness, well, the titanium aluminium nitride coating is about 5 gigapascals harder. And we can immediately see, if we look at this evolution of the wear during the cutting test, that the titanium aluminium nitride coating, i.e. the harder coating, is performing much less well and failing rather quickly, whereas the aluminium chromium nitride coating in this example has a long sort of period where the wear is quite minimal, and then when it does start to fail, then that's not an abrupt catastrophic process, that's still under control. So this is a much better situation for a cutting tool, so this delivers a lot more tool life. So that opens the question up as to what coating mechanical properties do you need? Well, firstly, in these applications, temperature is clearly important. So this is some data here taken from two different commercial titanium aluminium nitride coatings, presumably with about 50% titanium to aluminium in both coatings. And we can see the red curve has a higher hardness at room temperature, but its hardness starts to drop off, and at 500 degrees is rather low. Whereas the blue coating has a slightly more moderate hardness at room temperature, but it has much better thermal stability, and this has some potential benefits for different cutting applications. So the take-home message for that clearly is that if we simply test and do all our optimization based on the room temperature values, then we might be clearly in error. So there are a couple of key drivers forcing coating development at the moment for high-speed machining applications. Firstly, for environmental reasons, there's a trend to remove the coolant and cut dry, and secondly, for productivity reasons, there's a trend towards cutting up faster and faster speeds. So the example here on the left from Mitsubishi showing how over a 15-year period typically their cutting speeds increase by about a factor of 10. So these two things together cause extreme frictional heating on the tool. So this is a cutting tool insert. You can see in operation it's getting very hot. So under these conditions, it's vital really to know the mechanical properties of the coating at the temperatures in the application. So a previous approach to this essentially was to try to optimize based on a couple of different parameters such as hardness and oxidation resistance, but this is really an incomplete solution. If we think now in a little bit more detail about the cutting contact geometry and the heat flow that occurs during the machining operation, we can see here for the workpiece coming in from the left, coatings and the chips coming up here. This generates a lot of friction on the flank face, and this causes some increase in heating at maximum temperature here on the flank face here. So we put typically a 3 micron thick PVD coating to protect the cemented carbide substrate. And in the operation, one of the reasons why these coatings are so successful is that they can behave in an adaptive way and form thin tribo-films on this interface here. So the coating properties really has a couple of functions, firstly thermal and secondly mechanical. But it's not only important to think about the coating, you have to think about the entire tribo system. So the aim of the research I'm going to be describing in this webinar is how we can use high temperature mechanics really to improve our fundamental understanding of how these coatings work and the interplay between the mechanical properties of the coating and their microstructure and their ability to form and retain these thin tribo-films that protect against wear. So I'll start off by looking at monolayer titanium aluminium nitride-based coatings at room temperature. So looking at plasticity indices and showing how the extent of correlation between those and the machining performance in this case hardened steels, but fairly similar correlations occur for machining things like aerospace alloys as well. And then we'll move on to looking at more dynamic situations, looking at high temperature mechanics and dynamic nano impact. There were a couple of different case studies. Firstly, to anneal, if we anneal a high aluminium fraction aluminium titanium nitride coating at 700 degrees or more, and that can influence its tool life rather dramatically, and we'll try to understand why. And then I'll finish off with a more newly developed coating, which is this rather alphabet soup-looking type multi-layer coating on cemented carbide, which is shown to produce really amazing coating performance. So first of all, we look at plasticity. Typically, this is a nano-indentation curve as it happens on a typical tool coating, an aluminium titanium nitride coating. And in nano-indentation, normally we just use the unloading curve and we derive the hardness and the elastic modulus. It's a fairly well-established contact mechanics equation. So we're throwing away the rest of the curve from our analysis. That can be a bit of a shame. And as the areas you can see here, clearly there's some plastic work done in the indentation, there's some recoverable or elastic work done. And we can devise a fairly simple plasticity index, which is the ratio of the plastic work to the total elastic and plastic work. And that's a really useful dimensionless index. And this is the approximate correlation here between this index and the hardness modulus ratio, which is a key tribological parameter in a lot of different contact situations. So if we think about increasing the hardness modulus ratio in a contact for a material, essentially we have the effect of closing this hysteresis here, so we're getting a very hard and elastic film, something like a diamond-like carbon. If we decrease the hardness to modulus ratio, then we have something more like a soft metal of the sort of thing we might be machining. So schematically you can see how these trends affect the curve shape. And this is a particularly useful parameter, as I say, because it directly impacts on wear performance in a range of different applications. So this is some rather old work done actually for depth sensing micro-hardness measurements rather than nano-indentation. And this illustrates how 3 different coatings here, titanium nitride coatings, and how their relative wear intensity changes as a function of plasticity index. And we can see when we have a sliding wear situation, we need a relatively low plasticity index. If we get high plasticity index, we have a much greater amount of wear, which is clearly not a good thing. But in a more highly loaded adhesive wear situation, then the converse is true. So get different contact conditions are requiring different balance of properties in the coating to deliver improved wear performance. So moving on to nano-indentation now, this is some work we've done here at Micromaterials with a Berkovich indenter, typically indenting to about 40 millinewtons, and we can simply rank the plasticity index on a range of different materials from the uncoated substrate here at about 0.7 through to a diamond-like carbon coating here at about 0.3, and typically the sort of cutting tool coatings are in between the two. And there is some reasonable correlation. It's not perfect, but there's some reasonable correlation between the tool life and the different mechanical contact situations and this plasticity index in temperature measurements. So we can take that stage further and try and look at these different machining operations and determine an optimum value which gives improved tool life. And this parameter is a sort of shorthand. It's a rather indirect parameter, but it's still relatively useful. It's a sort of shorthand reflecting the relative importance of hardness and fracture resistance in the different contact situations. And one particularly clear thing to note at this point is under highly loaded interrupted contact, it's not useful to really aim to minimize plasticity completely, to have a very high hardness modulus ratio, to generate a so-called super hard or ultra hard coating, and that is really quite detrimental to coating performance. You really need a compromise between relatively high hardness together with high plasticity to give you the improved fracture resistance that you need in these sort of applications. So that was a rather indirect way to do it. Well, the contact situation itself involves an appreciable amount of temperature and an appreciable amount of high strain rates. And we can map out onto these two parameters with the nano impact test that we have in the NanoTest, and also with the high temperature capability. So this is a sort of temperature strain rate map, and it shows really that with the combination of these two we can really access much more closely the actual contact situations in the application. So back to this example you saw right at the beginning here of the cutting tool test on the steel. On the right now we can reproduce the shape of these curves, the relative ranking and all, fairly effectively with a simple nano impact test that takes really only a few seconds. And these things are pretty reproducible, and you can clearly see the difference with this one. Aluminium chromite nitride being much more resistant to impact fatigue, and this titanium aluminium nitride, after only a few impacts, you're getting this transition to a more extreme failure behavior, just like as you're seeing in the cutting tool tests. So the other key thing and the major focus of this webinar is the ability to measure directly at high temperatures. So in the NanoTest we have this dual active heating approach. We utilize our horizontal loading situation, and the sample sits sandwiched between a resistance heater just behind the sample and a resistance heater on the indenter side. And this creates what we've termed as sort of isothermal contact. And this separate active heating of the probe and the sample essentially minimizes or in some cases completely removes any thermal drift. So it allows you to test at really high temperatures, just as you can at room temperature. So there are some tricks in terms of doing it, and we're in the process of patenting that at the moment. If you want more details about how this configuration compares with the same approach with just heating the sample, which has been suggested is sufficient, then I recommend you look at this paper here by one of my colleagues, Mike, in collaboration with some people at Nottingham University. So we can use this high temperature test capability not just to do indentation, but to do a range of different tests, such as in a recent piece of work we've looked at using it for looking at nanoscale friction right up to 750 Celsius. We can also use it in applications for cutting tools, looking at microscale scratch and wear tests, nano microscale impact tests, and it's a work done in Cambridge University primarily. They've been looking at micropillar compression, and at Oxford University they've been looking at microcantilever bending and SPM imaging, really up to quite remarkably high temperatures. So in this webinar though I'll just be focusing on indentation, scratch and impact configurations. So we look first up at impact testing. So the example here is a couple of different tests, one at 25 degrees Celsius, another at 500 degrees Celsius, for a rather brittle titanium aluminium nitride coating. You can see at room temperature it's very brittle. There's one of these abrupt steps where the coating is continuing to fracture through the test. But at high temperature it's showing a much more ductile behavior. There is still a crack, but it's not as significant. So the wear effect at the end of the test is much less. And if we contrast the situation with a higher aluminium fraction, aluminium titanium nitride, indeed we get improved or reduced fracture probabilities during these type of tests, particularly at high temperature. And this is directly related to its cutting tool life, as in this example here. Again, cutting a different a different hardened steel here. Okay, so moving on to the first of the case studies. This first case study revolves around the influence of annealing a monolayer high aluminium fraction aluminium titanium nitride coating at 7, 8 or 900 degrees C in vacuum for a couple of hours. And this annealing has the effect of changing the microstructure. There's some grain coarsening that goes on, and it also changes the mechanics of the coating, as we'll see more on the next slide. And these two things together change the coating's ability to display the adaptive behaviour and changes its effectiveness in forming tribo-films. So now if we can look at some high temperature data taken with the NanoTest. If we first look at the effect of annealing when we cool the samples back down to room temperature, so these are samples tested back at room temperature, you can see the hardness of the four coatings is really very similar, but the differences become really quite marked as the test temperature increases. And you can see that the annealing has essentially stabilized the high temperature hardness of these coatings, particularly this one here that's annealed at the highest temperature. In contrast here, this as deposited coating, when you retest it at 500, really there's a rather dramatic drop-off in its high temperature properties. And this has a distinct bearing on its cutting tool life. So this is the first example here contrasting cutting tool behavior in a continuous high-speed turning application. And under these conditions, the hot hardness really in the coating is really vital. So there's a definite benefit. Remember, this one here is got the highest hot hardness, and this directly results in this much longer tool life. It's about twice as long as the as deposited coating here. What is particularly interesting though is if we change away from continuous cutting situation, if we start to look now at interrupted cutting situation, then we get some quite interesting trends. Now we can see a dramatic change in behavior. Now this coating now doesn't have enough plasticity to handle the interrupted cutting situation, and now its tool life is much lower than the other coatings. And we've done some high temperature micro scratch tests, and this coating again shows much lower critical load consistent with this result. So what is quite interesting now is if we start to compare the interrupted and the non-interrupted test conditions on the same graph. So here we've plotted everything relative to the tool life for that different test, for a given test, for the as deposited coating. So that's set to 1. And then we can look to see how, when we anneal it, what does that do to the tool life in the different cutting situations. So with a continuous cutting situation, then the annealing improves things, particularly for this one annealed at 900, because the hot hardness is the critical thing in this application. What's more interesting is that in this other application where the interrupted cutting, now this one is really very poor, even compared with the annealed one, and the optimum now is actually more like 700 degrees C. So we speculate that this annealing at 700 in this highly loaded interrupted cutting situation has essentially improved fracture resistance, and this improved fracture resistance enables the tribo layer to build up more effectively during the running in process, and allows this protective alumina-based tribo layer to form. And that formation of that tribo layer directly relates to tool life. So we can talk about plasticity. We can also talk about hardness modulus ratio. As you heard earlier, they're related, approximately inversely related. And this is typically what you might see as a function of temperature. If there's a range of different coatings that we can see, from that we can get these properties here, which it turns out these properties here are all related to longer tool life in this interrupted cutting situation. You can be too high up here or too low down here, and you get lower life. So clearly the nanomechanical test at high temperature is telling you something really useful that you can use to optimize your coatings. Okay, so that was it about monolayers. Now, for the rest of the presentation, if we start to think about a particular multi-layered coating, so this quite a complex composition, but you see that it's aluminium rich, and it's a picture here on the right. So this is essentially a hard system. So this is not designed as a lot of monolayer systems are designed so the shear happens in the softer ductile layers. This is not this design at all, so this is not a super hard system, and in fact its mechanical properties are rather similar to the two different monolayer constituents. But since that's the case, it's really interesting that it has a completely different cutting tool behaviour. So in this particular example, in this high-speed dry end milling of a hardened steel, then under these sort of conditions, a typical cutting speed might be about 200 meters per minute, and a cutting tool would really have to have a really good coating design to actually be able to cut at a much higher speed than that. And you can see this titanium aluminium chromium nitride monolayer actually can cut a little bit, so it's doing pretty well really. But the really remarkable performance is for these two here. You can see dramatic changes here in performance, not only for this monolayer, but even more dramatically for this multi-layered system. So we've investigated that with our collaborators at McMaster and elsewhere, and they've applied a range of different surface analytical techniques to try and understand what's going on in the actual contact situation. So this is a TEM showing the adhered workpiece material afterwards, and you can see the presence of this tribo layer here. It's really very thin. XPS shows that it's quite a complex chemical composition with sapphire and mullite-like phases in there. And with a range of other different surface analytical techniques, you can essentially show that the temperature here should be around 1,000, and here it might be considerably under 700. So there's a really rather dramatic temperature drop suggested across that interface. So it's quite different from a sort of thermal barrier that you might expect in an aerospace engine. So here this is a very dynamic system, and therefore different rules apply. So they act as a thermal barrier, creating this really strong gradient, and affects this effective heat redistributions. So our collaborators have tried to model this. So they've taken a system, an idealized system such as this, and they've looked at the heat flow into the body of the tool for an uncoated tool, then looking at titanium nitride film, then a titanium aluminium nitride film, and then this sort of mullite-rich tribo film here. And what we can see clearly is that all of these coatings improve the situation, and this one particularly works very well. So this one of the mullite phases. So nevertheless, though, the improved performance is not that monolayer, but it's the multi-layer, and the reason is that this has the improved high-temperature mechanical performance. So there's some work done here with a cubic boron nitride indenter, and you can see at room temperature, the blue one here, right through to 600, there's only a very small decrease in mechanical properties. So if we look now at hardness, we can see at room temperature the hardness is rather similar, but as the test temperature increases, the variation between these things grows. And we can see really, again, we're seeing really quite impressive performance out here, and even sort of it's over 20 gigapascal at 600 degrees, so it's really quite encouraging. In terms of scatter, I've not put it on this, but they were due to roughness, the scatter was about 15% in the measurements, and that did not grow as a function of test temperature particularly. So it's about the same at room temperature as it is at 600 degrees. So we look at this next slide, looking at two different other parameters, hardness modulus ratio and h cubed over e squared, which is a measure of the resistance to plastic deformation. So one thing to note is these coatings have relatively little plasticity compared to some of the monolayers we were looking at earlier, and something we felt that therefore there was something else going on, and it appears to be the multi-layer structure. So the high h cubed over e squared basically can give it high load support at high temperature, which minimizes the crack formation in the first plate, together with some this structural advantage, which gives it a route, this crack deflection across the interfaces for energy dissipation. So this is just an example here on a completely different system, but showing where a nanolaminate can deflect cracks in the scratch test, and this directly increases the critical load in the scratch test. So to conclude, I hope I've shown you that we can use high-temperature mechanics and the related techniques of nano-impact in the NanoTest system to give us a route towards an approach where instead of trial and error we have something more like a mechanical properties-based design rules that allow us to improve coating performance for these types of severe applications. We've been clearly able to show that for interrupted highly loaded mechanical contacts, for model air coatings you need to design for a combination of hardness with plasticity at temperature and not aim solely to optimize the hardness modulus ratio. The multi-layer coating we looked at has a combination of excellent elevated temperature properties with this microstructural advantage that together provides this relatively stable low-wear environment for the adaptive tribo-films to form and regenerate. And that, we believe, is what gives it the improved tool life. It has this distinct mechanical advantage where the high hardness cube to modulus squared ratio gives it this high resistance to plastic deformation and crack formation, together with this sort of nano-laminated multi-layer structure which enables this crack deflection across the interfaces, which relieves the strain and accumulation. Well, thank you very much for your attention, and if you have further questions, please email us at that email address there. And the panel discussion is going to follow from now.
Okay, so good afternoon. For the panel discussion, both myself, this is Mike Davis, an applications engineer at Micromaterials, and Adrian Harris, another applications here at MML, applications engineer, sorry, will be joining Ben. We've selected some discussion topics from the suggestions that you made when you signed up for the webinar. A lot of the suggestions fell into what we felt were sort of three main areas. So the first thing that we're going to try and discuss is the relationship between the H/E plasticity index and also the performance of coatings in scratch and wear tests to the actual wear behaviour of those coatings in real tooling applications. Secondly, and this is a subject which a lot of you were interested in, was the selection of indenter materials for these kinds of high temperature experiments. And tied into that, we also plan to have some discussion on different options for environmental control for these high temperature experiments. So the first of those subjects, which we're going to touch upon now, leads on nicely from what Ben was discussing in his presentation, and he's already discussed this a little bit. Just to recap, I'm going to start with this slide which you will recognize from Ben's presentation. So this is sorry about that. So this is a graph showing a typical indentation curve with information that we can get from these hysteresis curves highlighted. So in addition to hardness and modulus, we can also look at the elastic and plastic work done during that indentation. People have done work relating this to something which they've termed the plasticity index, so the plastic work over the total work done during the indentation. This is related to the hardness and modulus of the material being tested. So by increasing the ratio of H/E, we take a reduction in the amount of plastic work done during the indentation. Similarly, by reducing H/E, we see an increase in the plastic damage during the indentation. In the other example, we see an increase in the elastic recovery during the indentation. I'm going to pass over to Ben now to continue this discussion.
Okay, so in this first slide here, we're looking at the correlation between the plasticity index and the hardness modulus ratio. So we can see immediately that it's approximately 5 if you look across the entire range. But if you look in detail, you can see this is only really an approximate fit, essentially. So whilst this is a useful approximation, if you look in more detail, you'll see that this doesn't quite fit. Certainly, there's a deviation at the top end here, and if you look at down at this bottom end here, it's not so. We've looked at this in some detail, and we found typically that values of X tend to fall for a typical Berkovich indenter with some normal sort of edge rounding, tend to fall in the range of 6 to 7 for a wide range of different materials, from soft to hard metals and alloys. And in this example here, on a range of different nanocomposites here, you can see that they're quite clearly correlated, and there's X is about 6.4 in this situation. So we've also looked at about how this hardness modulus ratio and this plasticity relates to the performance in scratch tests. And what we found particularly is that there's different performance at high and low load. So at low load, you see distinct advantages in having this high H over E material with low plasticity. There's much more lower scratch depths essentially, so you're getting the contact remains much closer to elastic, and the wear is minimized. So that's quite a clear trend. However, when you start to look at more highly loaded contacts, things become a lot less clear. So this is some example of some unpublished work here we've looked at for a wide range of different coatings here, all on the same chart here. And what we can see here is that when H over E is relatively low, then we can improve the scratch performance by increasing this parameter. We're giving the system greater load support up to some sort of optimal values around here. But beyond that point, we get a distinct change towards a more there's a distinct drop-off because the films become too highly stressed, and there's actually a switch towards a sort of unloading failure as well in this regime. So this index is directly relating to the scratch and wear performance, just as it is in the machining test. And the where you want to be on this curve depends on the severity of the application. So if we look again at, just to recap with the cutting situation here, we're looking in terms of plasticity now. We can see that when we look at room temperature, we get these, for these aluminium titanium nitride coatings, this is a relatively constant parameter, but at high temperature you can see some clear differences, and there's a sort of sweet spot in the middle of optimum properties here that correlates with the improved tool life in these interrupted cutting conditions. So there's a direct relation again between the high temperature mechanics and the cutting tool life. Okay, so at this point I would like to hand over to my colleague Adrian Harris for the next section.
Okay, so Adrian's going to talk about the next subject, which is going to be indented materials suited for high temperature experiments. So typically for room temperature experiments, we use diamond indenters as the standard material for all experiments. As we increase the test temperature, the use of diamond becomes impossible in some situations. So what we're going to discuss in this next section are some viable alternatives to using diamond in indentation experiments. So I'll just pass over to Adrian now to run through this.
Okay. Okay, so thank you, Mike. I'd like to just give a bit more detail what Mike's just introduced for us there. So in particular, high temperature indenters, materials from which they're made, and environments in which we undertake high temperature indentation measurements. So I've just seen a question has come in that really touches on both of these things, so the stability of the indenter material properties themselves, and also a general question about in what environments we tend to undertake these measurements. So hopefully this will help to answer those questions. So indenters, typically we use a diamond indenter. Most room temperature work that you'll ever see will be completed with a diamond indenter. Diamond is usable at elevated temperatures. It's very, very dependent upon the sample material that we're testing. So diamond is soluble in a lot of materials, so particularly ferrous alloys. So what you'll tend to see with a diamond at elevated temperature in contact with a ferrous metal is that you will essentially dissolve the tip into the sample material. So the effect will be seen by the user of the instrument as smaller and smaller and smaller and smaller penetration depths as measurements take place, as the indenter effectively gets blunter and blunter. Diamond indenters will also react with oxygen in the air, particularly above 500 degrees Celsius. So, you know, there are some limitations. So what we tend to provide as alternatives are cubic boron nitride, which is very, very stable in terms of its reactivity with oxygen. It doesn't really react at all at the temperature range that we're interested in. It doesn't dissolve into the same materials that the diamond material dissolves into. Another possible material is sapphire. For many applications that's quite nice. It's very, very chemically inert. It unfortunately does soften much, much faster than either CBN or diamond with respect to temperature. So there are cases, for example, hard cutting tool coatings of the type that Ben was talking about earlier, which are not really measurable at very high temperatures with a sapphire probe, because the indenter is that much softer than the sample material itself. So it's just a couple of images to show you here. This is an extreme case on the left where a diamond indenter was used in contact with a ferrous alloy. And so you can see this sort of small flat end here. That's where the diamond used to be. It used to be just inside this hole and then cemented in position. It's gone, basically. So that was not a very long period of time, but about 500 C in contact with a ferrous alloy. On the right-hand side, a nice image here from Peter Hoseman at University of California, Berkeley, and that's a cubic boron nitride indenter. So this little bit here is the CBN. This is the metal in which that CBN is secured, and that's sitting there quite happily at 750 degrees Celsius. That would remain usable for a very, very long period of time, days, weeks, months, in air at those temperatures. So when you have selected the correct material for the job, you know, you can get some very nice data indeed. So this is actually some work that we did with some customers of ours at Georgia Tech, and looking at mechanical properties of glass ceramic material, which is used for a seal in a solid oxide fuel cell. These devices operate at pretty high temperatures, and so mechanical integrity, so hardness, elastic modulus, creep properties are very, very important and critical, in fact, to the reliability and longevity of those devices. So here we can see a rather nice set of creep curves going from room temperature up to 750 degrees Celsius. And we can actually see that the two samples that were submitted, one was given a thermal aging process of 4 hours, and the other was given a thermal aging process of 100 hours. The objective was to try to stabilize the mechanical properties with respect to temperature. And as we can see, a result of that longer aging process, the 100-hour aging process, is that the reduced modulus of the sample drops much, much more slowly with respect to temperature. So it's quite an attractive outcome for the fuel cell application. Take the next step up. The previous example, the glass ceramic glass solid oxide fuel cell, is quite a nice high temperature sample because it has a very, very low degree, non-existent essentially, degree of reactivity with oxygen. Of course, that doesn't count for all materials. So again, some of the materials that Ben was talking about in his presentation, in fact, have tungsten carbide, cobalt bonded tungsten carbide substrates. Now, there's a good example of a material which does oxidize quite readily above 600 degrees Celsius. So one solution to actually increase the testable lifetime of such a sample at high temperature is to test that in a gas-purged environment. So here we have an image of a system housed within a typical purge chamber. So these are a standard part we can supply when they're specified with an instrument. So we can fill this chamber with argon. Sometimes we fill with nitrogen, but that tends to be for not for high temperature applications. It actually tends to be for low temperature applications. The nitrogen is a very dry gas, and we avoid condensation on our indenter and sample with that. So with a couple of hours purging, we can get down to better than 1 part per thousand oxygen. So, you know, we're not down anywhere near vacuum levels, but as I said, what it does do is takes previously an unmeasurable sample and makes that measurable. So it gives us more working time. So the instrument remains quite nicely accessible inside these chambers. And one or two aspects of the instrument control which normally would be accessible in a regular non-purged environment instrument, I've actually got a nice remote control option that can be operated from outside the chamber without compromising the purge. Really, the ultimate solution for many sample types is to indent in a vacuum environment. So here we've got an image actually from Cambridge University. This is a project which is going for some time and now has pretty much completed the instruments in day-to-day use. So I think it's safe to say it was the first high-temperature vacuum nano-indenter. It's actually a very old micromaterials NanoTest instrument inside there, 20 years old in fact. So that was installed inside a chamber which they sourced themselves. So we assisted Cambridge University with this project over the course of a couple of years. So the project started in 2006, and I think in 2010 onwards it was regarded as fully operational. It's used from day to day. So this was really helpful to understand in more detail the technical challenges associated with putting a nano-indenter inside a vacuum environment and actually running nano-indentation measurements inside that environment. So we've built on that quite a bit as a company, and we now have something which is much more commercially available, a little bit more, we think, easier to access. And so this is actually an instrument which was commissioned in 2012 at the University of Oxford. So it's a pretty small footprint instrument. It actually takes up about the same floor area, if not slightly less floor area than a standard instrument. So the instrument within inside it remains largely standard. So that's quite nice because it means that an experienced user of a NanoTest system, or in fact a new user of a nano-indenter, wouldn't have to learn any special tricks or anything in order to actually run this instrument quite successfully. So this is being pressed into pretty intensive use now at Oxford University, looking at, amongst other things, the effects of irradiation damage, the near-surface mechanical properties of various materials which are candidates for nuclear fusion power applications. Just an example of the type of material we can get from an instrument such as that. What you see on the left-hand side of the screen here is a micro cantilever. So that's a feature which has been cut into a piece of silicon, in this case, a piece of silicon wafer, using a focused ion beam. So it's a beam of material which is supported at one end. Underneath that beam there is no material, so if we apply a load here we can bend that beam downwards. So some simple beam theory and some load and displacement data, so some stiffness data, we can actually start to calculate the elastic modulus of the material. So this image here is created using a 3D nano-positioner system, whereby the sample is scanned backwards and forwards. The probe, the indenter, is held on the sample surface under a very small load, so typically 1 or 2 micronewtons of load, and we end up developing a 3-dimensional image. From that image, we can then select a contact point at a known distance from the supporting end of the cantilever, and we can then apply a load ramp to it in order to create a flexure. So just a bit of information here to tell you about the size of the cantilever, so 4 microns wide. So in this particular case, the cantilever is at 700 degrees Celsius, and as you see, even at those temperatures, we get a rather nice image. So the right-hand side of the screen, we have the load and displacement data from 2 cantilever bend tests. So in the case of the blue trace, what happens is we get a pretty much purely elastic behaviour of the cantilever until a critical load when the cantilever snaps. So it flexes about half a micron and then crack, a brittle failure. In the case of the red trace, we start off almost linear. This cantilever is probably a little bit thinner than the one in the case of the blue data. Then we go into plasticity. This point here, there's not a fracture. The cantilever remained intact in this case. So the plasticity becomes extreme. We reach our 2 micron maximum depth limit, so we specify our instrument to stop loading as it reaches 2 microns. And in actual fact, that cantilever remained in fact just fully bent. So this is quite useful because in a relatively few number of measurements, we can actually start to pull out rather accurately things like the ductile to brittle transition temperature of a material. And if you can imagine that this sample could have received perhaps an ion irradiation process at the surface which could have modified its properties, then we may be able to identify that in our experimental data. So I think that draws us towards a close of this webinar. I'd like to thank everybody for attending. So we will be hosting more webinars, and information regarding those will appear on our website. So please do visit that to keep up to date with what we plan to do. Or if you have any particular questions, or you would like to suggest any topics you'd like us to discuss in future events, then please do let us know and contact us at info@micromaterials.co.uk. Thank you very much.